Welcome to lecture 3 of the optimization course. In the last lecture, we mainly focused on graphical solution approaches to optimization problem, and we discussed various important concepts, what is feasibility on graphical solution, what are the active constraints, and also showed you how to solve an optimization problem up to 2 variables using a graphical approach where we laid out a specific set of steps that you can do, for example, drawing the axis, then plotting the constraint functions, and then plotting the objective function, and then superimposing them to locate where the optimal solution point is. We will continue that sort of discussion also in this lecture, which is the graphical solutions to optimization problem part 2, and we will also discuss a lot of important concepts, and more importantly, towards the end of this lecture, we will focus on nonlinear problems also. In the last lecture, we mainly focused on linear inequality and linear equality and inequality constraints, and also the objective functions were linear. So how does the approach changes when the functions are non-linear? That is something that we will also see in this class. So let's get started. So the first thing that I want to discuss is focus on what are the different types of problems that you can encounter in an optimization problem. So let's get started with different types of optimization problem. So let's focus on the first problem type which you can encounter during any optimization problem. So let me begin with focusing on giving you specific examples where I'm going to lay out the objective function and the constraint, and then using the approach, the graphical approach that we listed out in the previous class, we will plot all of these things together and see where we end up. So if our problem is something like this, where we have an objective function where fx is equal to x1 plus 2x1, which is what we want to minimize, and we have set of constraint, for example, g1, which is inequality constraint, and typically, in optimization problem, when you have g, and this is the typical notation, this means that this is an inequality constraint, and typically h is used to represent equality constraint. Okay, and that's why you see we have written G1, which means the first inequality constraint that we are handling, which is given by this equation here. So that's one inequality constraint, but as we have seen, we can have multiple equality and inequality constraints in a given optimization problem. So here is the second one with respect to this problem. And then we have also the bounds on x1 and x2 variables. So the x1 has to be greater than 0 or greater than or equal to 0, but it has to be also restricted and it has to be less than equal to 5 2. So that's one bound. Similarly, there is also a bound on x2 variable, right? So that has to be between 0 and 5 2. So one of the things that you can see from the notations that we have written, this is not in negative null form, right? So first of things that you should do, and this could be a good practice form for you, where you can take this set of equations and you can write this whole set of equation in negative null form, right? And that's not the case, but the first thing you should do is write the negative null form, and that's something that we have discussed previously. Okay, so so let's take this problem and see how this problem looks graphically and what intuition we can gain from that plotting of this problem itself. Okay, so again, we will follow the same steps that we have laid out previously, which is basically we will do the scales, right, and we will have different constraint plotted. So this is the first G1 constraint which you have plotted, and then we have also determined that this side of this constraint is infeasible and this side is feasible. That's why we have shaded it. So this is the plot of the constraint 1, G1, right? So this is the plot that we will get. Similarly, we'll go ahead and plot all the other constraints that is there, right? That's the step 2. So let's take the second constraint, and if we plot that second constraint, we will have this plot. Now remember, the interesting thing in this one is for this constraint, the feasibility is on this side. So all the side, or if we have this constraint right here, I can take this, and this region is feasible according to this constraint G2. Whereas this side, if I take this side, this one is infeasible according to the constraint G2. So this one is G2. According to G2, this one is a feasible region, but this one is infeasible region. Okay, so that's an interesting thing that we should note, because that will help us in identifying the solution later on. So those are the two G1 and G2 constants that we have plotted. Now we will plot the, basically the two bounding, right? We have the two constraints, which was like the x1 has to be less than equal to 5 and it has to be less than equal to 0, right? So this equation was there. Similarly, we had also this equation where this has to be 5, and that essentially gives me this bounding box, right? This square type of bounding box that is out there, and that is what is causing this shading. So this are representing these two conditions, right? So the overall graphical plot to the previous problem with respect to the constraint is given here. So if you look into this constraint and the plotting of the constraint, one of the things that we need to determine that where is the feasible region, and this is something that we have done with respect to the previous problems too, the problem in the previous lecture. So now let's look into this problem, right? So according to this plot, right, the solution has to definitely lie in this, rectangular region, right? So sorry, this is a square region that we have. It has to lie inside that. Now let's look into how these two constraints, G1 and G2, affect the overall solution. So if I look into this, I know this solution has to lie in this box, but if I pick G2, which is this constraint right here, if I pick G2, G2 is telling me that anything which is basically below this line in this direction is infeasible. So the only feasibility if we just add G2 is something which is like along this line. So we go from here, go here, and go here, and come back. That's what is feasible remaining if we add G2 on top of the constraint which are handled by this 4 square region. Now if you look into G1 constraint, right, what is happening with the G1 constraint? The G1 constraint is saying that, that everything above this line, this region, everything above this line is infeasible. Okay, whereas this region, everything below this line right here is feasible. So this one is feasible, whereas anything above is infeasible. That's what this constraint G1 is alluding to, right? So now we are in this catch scenario that, okay, everything above this is infeasible, so everything becomes infeasible here, only this thing is feasible, but now this tells me that everything below this is infeasible and everything above this is feasible. So if we combine this information from both G1 and G2, it turns out there will be no feasible region left out. Okay, because everything above this is infeasible, right? So all this whole area is infeasible, and according to this constraint, everything below this is feasible. So this whole square region, which was feasible because of the 4 constraint on the x1 and x2 variable, becomes infeasible because of these 2 constraints that are there. Simultaneously, these 2 constraints acting makes this whole problem infeasible. So there is no feasible solution. So this represents a scenario where you have no feasible solution because both these constraints are elementing with. If you did not had one of the constraints, let's say G1, then in that setting you at least have this region which is feasible. But because you have G2 and G1 is saying that, okay, anything above this is infeasible, that is making the whole feasible space essentially a null space, or there is no solution in that space itself, right? So this problem essentially falls into that category where you do not have any feasible solution and there is no feasible region at all, and you cannot find any feasible solution to this problem. And this class of problems are known as infeasible optimization problem, right? And that's what will be the first category of, okay. If that's the case, what you need to do is you need to re-examine the problem formulation, and there is some issue with the problem formulation, and you have to correct the problem formulation in such a way that at least you have the notion of feasibility, or at least you arrive at some feasible state. Because you remember, you have to optimization as a framework of selecting, few good example problems or few good solutions out of infinitely many good solutions. For few good solutions to exist, there has to be some feasible solutions that exist. If that does not exist, that means your problem formulation has some issues and you need to work on that, and you need to probably reformulate your problem. Okay. So with that, let's move on to problem 2, or the second type of problem that we can see in optimization.